great pleasure for me to come here. The last time I came, it was 4 years back, and I could see the same kind of enthusiasm and a lot of participation from the audience that time. And it's very happy to see that the activities of the Bangalore Science Forum is continuing very well, and as said here, this is the 2521st talk, I think, if I remember the number right. Yes. Yeah, so this is amazing. I mean, I don't think maybe nowhere in the world that there could be such a record. So I would like to congratulate those at the help of the Bangalore Science Forum for this well achievement. And I was just reminded of what happened today morning. When I came into my office, my colleague was very excited, and she asked me to come to her room, and she showed me on her computer some images of Pluto, the latest images of Pluto, because it was released only yesterday also by NASA, and these are the photos, the best photos ever we have of Pluto, because this spaceship, the spacecraft, the New Horizons, is actually very close to Pluto. It's like about 70,000 kilometers or so. It's very close by the scale of our huge solar system. And she was showing me, and she was very excited. And I realized that somehow my son has missed it. He didn't tell me anything about it. So when I go home tonight, I have to tell him that, look, NASA has this new information. So in connection, we also discussed something else in the institute in the first week of June. That was the following. For some reason, for our PhD program, we hardly see students from Bangalore coming for the interviews. And this is a tendency that we have been seeing for the past many years. So if we look into the students who get admitted to our PhD program, I think in IAC also this is more or less the same. It is mostly from other states. For some reason, people from Bangalore don't really seem to be too keen to do a PhD in the sciences. Probably because there are many other avenues open here. Like, even before you graduate, there are ways in which you can get a good job and all that. So maybe these are the reasons why I think slightly less interest among the Bangaloreans to take up a career in science, despite the fact that we had great people like C.V. Raman and many others in this place. So probably the seniors here should, I think, enthuse your younger ones to take up science as a career, because it's a very promising career, very fulfilling career. We are all very happy. Most of us whom I know, from our profession, we are very happy to have chosen this career. So now coming to the topic of today's talk, this is about plasmas. Well, what we know about plasmas is that plasma is the fourth state of matter. This is what we learned in school. This is true. But there are ways in which we can generate a plasma. We can create a plasma in the laboratory, which has become easier these days because of the availability of hydrolyzers. So that is the way we generate plasmas in our laboratories. And the advantage is that you can generate a plasma and you can study the plasma. And that will give you a lot of information about what is happening in other parts of space, for instance. Like we know a star also is a plasma. So these kind of studies are aptly known as laboratory astrophysics. So you can do astrophysics without even using a telescope. Well, there are differences, of course. I'm not claiming that the astrophysics that we do by directly observing stars and galaxies is a bit different from the astrophysics, of the laboratory astrophysics we do in our labs using laser pulses. But nevertheless, this is a very interesting thing. And, well, I don't really need to tell you anything talking about the Raman Research Institute. I'm sure that all of you know about the place. And in case anybody doesn't know, just for the sake of completion, this is very close to Lake Circle, and it was founded by C.V. Raman in 1948. This is some photographs of our place, and this is a place where science is fostered and a lot of discussions happen, and we do research. We don't have master's courses or such courses. We only have the PhD as a course, as an academic course, which is an offshoot of our research program. And so the areas of research are astronomy and astrophysics, soft currents matter, which was bigger discussed earlier, theoretical physics and light and matter physics. And we are about 38 faculty members approximately, about 60 PhD students, and about 70 visiting students. And our present director is Professor Raman. He is an astronomer, and our funding is from the Department of Science and Technology, Government of India. The outline of this talk will be, I will briefly tell you about the basic plasma parameters, then methods of producing a plasma in the laboratory, then laser-produced plasmas, then atomic processes in plasmas very briefly. Then I don't think I'll get the time to go to spectroscopic and time-of-flight studies of nickel and silicon. These are the plasmas which we studied recently, but I think that would be a little more specialized and may not be really useful here. So then we will go to the conclusions. So this is, if you look at the states of matter, we know there are solids, liquids, and gases. So a solid is that, what we see there. There is a lattice, and the molecules of atoms, they are arranged in a good order, and they cannot move individually, but they can move as a whole. So that's what more or less makes a solid. When we come to liquids, we see that the individual particles have freedom to move around, and it has properties which spring out of this motion. And when we come to gases at a still higher temperature, we can see that these gas molecules are really moving around very fast. The density is lower in comparison to what you have in liquids and solids. Now from there, increase the temperature, we can go to the next state, which is the plasma state. So, if you look at the electron temperatures, what I mean by electron temperature is actually the energy of the electron, the kinetic energy of the electron. So if you look at that, you can see, I mean, this is a scale. So it is given by half mv square, where v is the average velocity, by 2 kT, where k is the Boltzmann constant. And the temperatures are in the order of, I mean, it can, for plasmas, it starts somewhere around 10 to the power of 4 Kelvin, and from there, it can go higher. Whereas for solids, it can actually come down to, as we know, I mean, it cannot hit the absolute zero, but it can come very close by making use of cooling methods. There are different cooling methods. Even in our group, there are experimental techniques called laser cooling. You can use lasers for many things. Even for DVDs, you are talking about storage in DVDs. They're also in a DVD player, in a CD player, all that. We actually use lasers to read, to get the information back from the system. So lasers are very versatile in that sense. These are the temperature ranges and the electron energy ranges that we are talking about. So what is a plasma basically? A plasma is actually a collection of charged particles which are sufficiently dense so that space charge effects can result in strong collective behavior. So we have a system where you have ionized material, right? So therefore lots of electrons and lots of ions. So this is the primary requirement for a plasma to form. And the second thing is, in a plasma, the electrons are essentially free, or there are lots of free electrons, and they can behave in a collective fashion. This is not true with a non-plasma. If you take a gas which is not ionized, it is not a plasma. In such a case, if you excite this gas by means of some mechanism, it can be light, it can be heat, you will not see that there is a collective excitation happening to the electrons, or they don't collectively jump to another energy state. It is more or less an individualistic process. But in a plasma, because the electrons are really free, you can really move them around. I mean, you can collectively force them to do something. So that this is one of the characteristics of the plasma. There is a collective behavior of the charged particles. Then it also is quasi-neutral. What it means is, if you look in a plasma, locally you will see that there are charges. Charges are separated. But if you look in a higher dimension, I mean, in a higher volume, in a larger volume, then you can see that it is neutral. So this is what is, I think this is a statement of the obvious, because when you ionize something, there will be equal number of electrons and ions. So overall, there is going to be a neutrality in the system. But because this distribution is not going to be uniform, if you take any particular region of the plasma, you will see a difference in the number of positive and negative charges in that local volume. That is what we mean by quasi-neutrality. So to characterize a plasma, there are plasma parameters. So these are the density of the neutrals and the electrons. Once you ionize your gas, or you can ionize even a solid, you will see that very shortly. Once you do that, what is the density of, what's the number per unit volume of ions, what's the number per unit volume of electrons? So these are the parameters which tell you about the density of the plasma. Then there is energy distribution, that's the temperature of these particles, how fast are they. It will depend on the way in which you generated your plasma. Then there is something called the degree of ionization. So if you have 100 atoms, for instance, let us say you ionized only one atom out of it. So the degree of ionization is only 1%. Actually, we will see that in many cases, particularly in laser-produced plasmas, the degree of ionization is not very large. It is only something like 5%, 6%, that's all. But that's more than enough for our experiments to be performed. Then the plasma temperature, it can be the ion temperature or the electron temperature. We talk about both. Then there is something called the Debye length, and this is the range or the distance up to which any single charge in a plasma can exert a force upon another charge. So one can think of a device sphere, and it has a certain radius. So all these things can be calculated if you know the plasma parameters. And so these are, I'm not really going any deeper into these things because we need these concepts to really calculate things for a plasma. Then there's also something called plasma frequency. This is a resonance frequency of your free electrons in the plasma. So depending on the plasma, the material from which it was formed, you will have a plasma frequency. That's a resonance frequency at which the electrons can absorb maximum energy from a certain input. So we will use all these concepts when you generate a plasma in the laboratory. So now coming to how to diagnose a plasma. Because once you generate it, there are certain techniques by which you can do it. So we usually use spectroscopy, but there are also some other techniques we don't use here. So these are like laser scattering techniques like Thompson scattering. Interferometry, we are planning to start this work. We will do it very soon. Then polarimetry, shadowgraphy also we are likely to do. Because you need different kind of equipment for doing all these kinds of experiments. Very recently we purchased, just last week, we purchased a new spectrometer with which we hope to do interferometric experiments. So these are the experiments by which we can characterize a plasma and diagnose it. What we mean by diagnostic is that you find out all the parameters of the plasma which you have created, and from that you can get a lot of inferences. Then there are also electrical measurements like Raman probe. It's also possible. Now, there are many natural plasmas in our neighborhood. For example, the sun and its atmosphere, the solar wind, the magnetosphere and the one radiation belts, the ionosphere, the plasmas beyond the solar system. So this is a plasma which all of us know about. This is lightning, and this is extremely powerful, much more powerful than we actually think. Typically lightning discharges about 30,000 amperes of current at up to 100 billion volts. So these are huge numbers if you really look at it. And it emits light, radio waves, X-rays, gamma rays, etc. And plasma temperatures in a lightning bolt can approach 28 kilokelvin. This is fairly high. And electron densities can exceed 10 to the power 24 per meter cube. Both these values are high. That's why we know about unfortunate people who get struck by lightning, and I have seen some videos, and it's a very gruesome sight. I mean, they become like they become carbon. They just get reduced to carbon, black. So there is also a lot of plasma in the universe. Like this is a galaxy, a very nice galaxy to look at, and each of those stars is a plasma bomb. And we know there are billions of stars in any single galaxy, and there are billions of galaxies in the non-universe, and it is said that there are billions of universes. So therefore, we really don't know. I mean, and as I started, New Horizons took how many years? 9 years, because it started off in 2005. The spacecraft, which is actually going at a very high speed, it took 9 years even to reach Pluto. So, I mean, the scale of things that we are talking about is something which is impossible to grasp. Now, we know we have seen plasmas in various occasions. So, this is plasma by glow discharge. So, what is done here is you will have a vacuum tube, not exactly vacuum tube, an evacuated tube. I'm sure the seniors here will definitely know what is a vacuum tube, because the old radios, even when I was a boy, like I still remember the vacuum tube radio. It used to be called the valve radio. So the valve radio was there at our home, and I think by the time I was in the 8th standard or so, the valve was disposed of and the transistor came. The transistor radios came. And now there is actually a going back to the tubes or the valves, particularly by the audiophiles who want to really, I mean, there is this community called audiophiles who want to make the best music out of electronic equipment. So it's like going in a circle. You start with the valves, then you say that, oh, these guys are not good because, I mean, they emit a lot of heat. They need a vacuum. If it falls down, it breaks. So there are so many issues. You need high voltage and all that. Then they found transistors, which are extremely good. So now you make transistor amplifiers. Oh, they are very good. All that. Finally, people say that, okay, transistors are a problem. The clicking characteristics are not good. So you come back to valves, and I have really seen some of these new valve offerings. I don't think we have them in India yet, but this is quite a craze in the US now. So there are communities, online forums and all that, where people discuss a lot of audio, and some of these are very good actually. So I mean, that's the story of tubes or valves. So we have seen these neon tubes or neon lamps, little neon lamps and all. This used to be the standard in a lot of electronic equipment earlier instead of LEDs. LEDs came later. So LEDs are brighter, cheaper, more energy efficient. So those are almost completely remove these guys from those displays. But still we have on display signs and all, we have these plasma displays. So here this is a glow discharge, a small half-inch neon lamp, which you see on the left side. And what you see on the right is a very interesting device. I have asked many people, have you ever seen this? Surprisingly, Most people said no. Even very senior people told me they have never seen this, but I have seen one. When I was starting my PhD, there was a certain instrument in our laboratory which actually had this kind of a display. So this is before all the, for some reason it must have been a very ancient equipment, because by that time the digital displays were already there. So, but this guy is very peculiar. It has all the letters from 1 to 9 inside as different designs. So, as required, it can light up any one of them. So, let's say you want to say 230.0 volts. Then 2 will light up in the first tube, 3 will light up in the next one, 0 will light. So it was like that. So only thing is this is bit bulky and huge. So it's called an XE tube. I don't think any instrument uses this anymore because there is not any particular advantage of using it. Now here is an arc display, an arc discharge. This is a bit different in the sense that this operates at the normal atmospheric pressure. We have seen this where welders, when they do welding and all, they use this kind of stuff. So there are two electrodes. They come very close. When you bring them very close, if you apply a high voltage to that, the air in between will get ionized, and therefore it can sustain an arc discharge there. At MSc Physics also there's an experiment to, there's an iron arc. You generate an iron arc and then take its spectrum. We have done this. So in those days it was like you have to use a spectrometer, a very conventional spectrometer. Then there are films which you have to put the film sheet inside. So you get all those lines the same way Raman did his measurements. So, and then there is, research students were more fortunate. They could use an instrument called microdensitometer. So they take the film out and put it in the microdensitometer. So then you can find out the values of the spectral lines, the wavelengths very easily. But MSc students are not allowed to do that. We had a much more cumbersome way of calculating those things by, if I remember correctly, something called Hartmann's constant or something. I don't know whether these experiments are still there, but these were very good learning experiments. So they were very, very good, though they were not very easy with the old kind of equipment and all, but a lot of learning they provided. So this kind of discharge was first demonstrated by Sir Humphrey Davy by using two electrodes. He put them together and he pulled them apart a bit and he could demonstrate that it works. Okay, so there are many types of plasmas in the universe. Whether a plasma is real hot, if you put your finger in a plasma, will it burn? That depends on two things. First of all, the temperature of the plasma. Secondly, how dense is the plasma. So you can, for example, interstellar space is actually in plasma state. Not because it has high temperature, but because it is ionized. So there are three criteria for a plasma to be existent. For an ionized gas to be existent. So if these criteria, actually interstellar space meets these criteria. So therefore it is a plasma. But it's not a plasma like the sun. Because if you look in this graph, you can see that the sun is at the right top and interstellar space is on the left bottom. So it is like very high temperature and very high electron density in the sun, low temperature and low electron density in the interstellar space. Because in space, the density is like 1 ion per centimeter cube. It is so low. Well, now coming to whether we can generate a plasma in the laboratory. Can we do it? We use lasers for this. There are also other methods. So if you take a standard atom, so it has a core, it has a nucleus, and then there are electrons which go around. So let's think about the valence electrons which are free and relatively free compared to the inner electrons, which are very tightly bound to the nucleus. So in almost all materials except metals, even the valence electrons are really bound to the nucleus. In metals, you have the conduction band where they have some freedom to move around, but even then they are not really out of the influence of the nuclei in the lattice. However, considering a dielectric where you have the electron nucleus system, it is possible for us to excite the dielectric atom such that the electrons oscillate. And when we use it using normal kind of light, like let's say I'm trying to excite something with this kind of light, which is actually not very intense compared to much more powerful sources of light, then this dielectric atom behaves like a simple pendulum, or it's a harmonic oscillator. And all the properties like optical properties like dispersion, which includes refraction and absorption as the real and imaginary parts of the susceptibility. So those things can be derived by considering a dielectric atom as an electron, as an oscillating electron. We don't really assume that the nucleus is oscillating because the nucleus is much more heavier compared to the nucleus. So we can assume safely that it is standing still. But as you increase your intensity, like instead of using sunlight or tube light or something like that for exciting your material, let us say we are using laser beams for excitation, powerful laser beams for excitation. Then what will happen is that the electrons will be moved a little further away from their orbitals, and in such a case, the system will move out of the linear regime. It is not a simple harmonic oscillator anymore. It becomes kind of an harmonic oscillator. Now we know that an oscillation which is not harmonic, not simple harmonic, will generate frequencies at the harmonic numbers. So you have a fundamental frequency plus its harmonics, like second harmonic, third harmonic. So those who know about music, or those who have learned some music, know that the timbre of a certain instrument, like for instance, we know in music festivals, we know first before they really start the performance, the players will actually sit there and they will tune their instruments. So we can see that the violin is tuned to the harmonium, and if there is something else that also is tuned like that. So it's easy to note that the pitch of the violin, when you say it is tuned, what you mean is that the frequency of the violin, that particular note, whatever note it is, let's say C or whatever, so that particular, I don't really know music. So that particular note will be the same note on your keyboard or your harmonium. That is when you say that the pitch is matched. But it's very obvious that the sound produced by the violin is very different from the sound produced by the harmonium. And we also say that the frequencies are the same. So this cannot be true for pure sine waves, because for a pure sine wave, 1 kilohertz will be the same from any instrument. I say 1 kilohertz because you were mentioning, well, I think Dr. Kamla mentioned Akashwani. So before the station opens in the morning, you hear this note, a note for some time, and that is the 1 kilohertz pure sine wave tone. So that has to be the same irrespective of any instrument. But what makes a harmonium distinct from a violin is the fact that the harmonics have different kind of amplitudes. Even though the fundamental is the same frequency, the harmonics like 2 kilohertz, 3 kilohertz, 4, they will all be there. And they have a different ratio. So this is what actually makes each instrument different in its timbre. So this is what we call timbre. Now, in a similar way, the generation of harmonics will happen optically also in dielectric interiors. If you put in too much of, there are some conditions for this to happen, like you have to put in a little more power into the system because this is an electron nuclear system, very different from a vibrating string. So that can happen, and this regime is known as the nonlinear optical regime. One can go even further. When you go even further from here, you see that the system is ionized, or the electron is actually ripped away from the parent nucleus, and that is the regime of the plasma. So you have to ionize your system. You have to put in a lot of intensity in your system so that the electron is really pulled out of the clutches of the nucleus. That's when you generate a plasma in the laboratory. And we can do this using lasers because lasers have a lot of electromagnetic power in that. We know light is electromagnetic radiation. And lasers are very high intensity, so the EM radiation is very intense. So, intense light fields are like 10 to the power of 12 to 10 to the power of 16 watts per centimeter square. Here, the perturbation approach, I mean, we all have, those who have done BSc physics, they have studied the perturbation approach in quantum mechanics. So that's a way, if you want to study a system, that's one of the best approximations to start with. You write a Hamiltonian for your system, and then you put in a perturbation Hamiltonian term there, and then you solve your equation. So these perturbation regimes are applicable. It's applicable in the case of linearity, all kind of linear behavior, and a little bit of nonlinear behavior. But when ionization happens, this is not the case anymore. And you need these kind of intensities to ionize your system. So how do I generate an intense electric field? I can use a very powerful laser. It cannot be a low power laser like we have these. I think I can use this. I think it doesn't work. It's okay, it doesn't matter. Okay. So the way I generate an intense field is by using a laser. In this case, this is 50 millijoules energy, that's quite high, and for a laser, and 100 femtosecond pulse width. We know femtoseconds are extremely short, so these are very short laser pulses. And so this will give us a power of something like 0.5 to the power of 12 watts. So now I can focus this using a lens, and once you do that, I mean, I can use a normal lens to focus it down to something like 20 microns. So once I do that, I'm actually concentrating all my energy, all my power into a very small region. And when I do that, I get intensities in the order of 10 to the power of 17 watts per centimeter square. Now this intensity corresponds to something like 10 to the power of 10 volt per centimeter in electrical terms. We know that this is very high because what does it really mean? Just imagine a capacitor with the plates separated by a distance of 1 centimeter, and imagine we are applying a voltage of 10 to the power of 10 volts to it. So that's a kind of, it is, and if you put an electron in there, you can imagine what will happen. It will fly off like to the anode. Okay, that's what, same thing will happen here also. So, and it's also good, it's also instructive to compare this with the Coulombic field inside a hydrogen atom. We know about the hydrogen atom, it's the simplest, smallest element. And we know that there is just one electron which moves around one proton. And these are very close to each other because we know the distance from the proton to the oneness electron is very, very short. Because of this very short distance, actually the electric field within a hydrogen atom is extremely high. It is like 10 to the power of 9 volt per centimeter. It's very high. We usually don't really appreciate the kind of electric fields which exist within a hydrogen atom or any other material for that instance. So I really need this kind of a powerful laser to generate an electric field which can match that of the hydrogen atom. But once I have this, if I have this, which is now common, now it is possible. 10 years back it was not that easy, but now it's fine. I mean, these lasers are available. Only thing is they cost a lot. Typically can be something like, for something like this, it can be 2 to 3 crores of Indian rupees. They are quite expensive. Okay, but I can use them for these purposes. So I generate a plasma like this. For generating this plasma, I haven't used such a costly laser. It's not really necessary because you may have a target which will get ionized much easier compared to the hydrogen atom. In the hydrogen atom, just imagine the electron is so close to the nucleus, so it's very hard to pull it out. But if you have a much bigger atom, then the nucleus is at the center and your valence electrons are far away, so it is much easier to ionize them. So therefore, you don't really need that kind of an expensive laser to ionize, let's say, a metal, for example. I can keep copper, aluminium, something like that, as my target, and use an ordinary laser, not like this is not enough, but there are lasers, nanosecond lasers, which you can buy for about 15 lakhs or so. So those instruments, I mean, these are relatively cheaper stuff when you are talking about high-power lasers. So once you have something like that, then you can generate a plasma from a metallic target. Because as we know in metals, the electrons are pretty free, so it's easy to ionize. So that's what we do. And here, this is a carbon target. So this is a photograph which we took from our own setup, from our experiment in our laboratory. So on a carbon target, you use a laser pulse and you generate the plasma plume. The plasma, we say that it's a plume because it sort of expands from the point of the radiation, and it will be a bright light which exists only for microseconds, and after that it will die out. So you have to make all your measurements within those microseconds. Yeah. But that's not difficult, because now we have electronics which is very fast. I told you about the spectrometer which we bought last week. I think it was, well, I better not tell you these prices. It's very expensive, 50 lakhs or so. So the thing is, but it's because its time resolution is so high. I'll show you some plasma photographs as we go along. So we can take photographs of the expanding plasma with a resolution of 2 nanoseconds. 2 nanoseconds is so short. In 2 nanoseconds, light will travel only 2 feet. You know the velocity of light. Light will travel only 2 feet in 2 nanoseconds. But actually, 2 nanoseconds is a very long time for us now, because we have femtosecond lasers. So that's the way we are going. And we can be really happy that our country actually has all these instruments. We have all these technologies here. So when we know these things. We are not like some other countries, particularly in the continent of Africa, for instance, where they can be easily fooled by the developed nations on many pretexts, but it is not possible with our country. Because at least we have the knowledge, at least we can understand their language. That much we have achieved. So, therefore, this is the plasma proof, and we can generate different types of, depending on your target which we use, we can get different kinds of plasmas. Now, this is the process, how plasma is generated. First, we have the very intense light field E, because I think I didn't mention this. Light is electromagnetic radiation, so we have the electric field oscillating there. And it is this electric field which actually rips the electron, because electron also is a charge. The electron will move in the electric field. So if the field is very strong, it will take an electron along with it. That's what happens. So because of the intense light field, ionization happens, then the ions, the electrons actually travel very fast. They will pull the ions. This is called the Coulomb pull. So the ions also will move very fast. Then they will collide with each other. When the ions collide or electrons collide with other neutral atoms and molecules, they also get ionized. So this kind of a chain reaction. So finally, the plasma, we get a very good plasma in our system. And then the energy gets redistributed because whatever energy came in, it actually gets redistributed in the system in various forms. So if you look at the emission part, that's what we mostly do. We do spectroscopy. We look at what light is emitted, we measure it. So we can see particularly incoherent and coherent emissions. So coherent emission is this we haven't measured until now. But we have plans to do this. Because if you really want to generate high harmonics, it's actually high harmonic generation, we need slightly more powerful lasers, and we have the plans to upgrade our system maybe within the next 2 to 3 years so that we can actually do coherent X-ray generation. So until now, what we are doing is looking at incoherent emission, that is fluorescence or light emission in various ways. In the ultraviolet, in the visible, and also in the X-ray region. So we have detectors for all that. We can measure all these things. Now, if you start with a femtosecond laser pulse, then you can get femtosecond X-ray pulses, femtosecond gamma ray pulses like that. So this is very interesting. And the physics here is very interesting. Like, if you really go down to something like 4.5 femtoseconds, then you see that you don't have one wave. You know, light is wave, right? So can we imagine a wave which is not complete? Because as I told you, in 1 nanosecond time, light will travel 1 foot. Now, from nanosecond, you go down to picosecond, go down to femtosecond. So we have come down by 6 orders of magnitude in everything. So in distance also. So now the light cannot really propagate 1 foot. Calculate, you will see that the light propagates to a distance which is less than its own wavelength. And we have a problem. What is it? What kind of an entity is that? So this is like, I have a colleague who works in quantum gravity. So I guess you might know what is quantum gravity. These are two concepts which are very difficult to reconcile with each other because we know gravity is the theory. Einstein's general theory of relativity deals with gravity, and he speaks about huge scales of macroscopic stuff where, you know, gravity is nothing but ripples in space-time. That's what gravity is. It's a very different concept compared to Newtonian gravity. Now, quantum mechanics is exactly on the opposite side of the spectrum, where you are talking about things of the size of electrons and less than that and all that. How can we reconcile these two things, and what's the need for reconciling these two things? The need actually arises from the idea of Big Bang. Because according to our belief now, the universe formed by a Big Bang. And the Big Bang is considered to be a singularity. Singularity means the laws of physics will break down. Because now you can imagine going back in time. So we compress the non-universe, compress it, compress it, compress it. Finally you come to a size which is like a point. It has no volume, basically. So the entire universe has shrunk into something with no volume. Then the laws which are applicable are those of that of quantum mechanics. Just because of the size scales. GTR doesn't apply anymore. What is worse is that just at the moment of Big Bang or just before that, there is no time and there is no space. These things don't exist. So how do you solve your equations? Because you look at any equation in physics, there is either a time term or there is a space term. Now you are faced with a situation where time and space are not born yet. And you have to solve, you have to write equations for it, you have to solve equations for it. How do you do it? This is a very difficult problem. So, my friend decided that he is not taking any PhD students, because if you take a PhD student and give him a problem like this, he will take 5 years even to understand the problem. So his life is lost. Okay? Before he submits his PhD thesis, it will be 15 years. And then you have to, then it's a gamble. I mean, you don't know whether the thesis will be accepted by the examiners. So he decided to work all by himself. Because he says it's much easier. Just because of the magnitude of the problem that he's attacking. So anyway, so it's like this. I mean, here we have such fundamental conceptual issues which normally doesn't arise in normal life. We are pretty cozy and comfortable because we deal with macroscopic phenomena. We deal with several waves, but we don't really deal with half a wave, 1/4 of a wave, and all those things. Anyway, these are some very interesting problems which people are attacking now, like how to deal with these situations. And there are very interesting results which are coming. So, there are different emission processes in the cosmos. I may not really go much into this. There are, because the energy states of the electrons in plasmas are of different kinds. Most electrons are in a free state, so it's called a free state. Then there are many neutral atoms also in the plasma, which are in the bound state. So the free electrons can emit radiation by getting recombined to an ion, and even within the neutrals itself, there can be emissions. So all these spectral emissions will be there when you make a spectral measurement of your plasma. So here, I am making a plasma in air. You can see a spot here. So it is very much like, it's very similar to the way of seeing sun from Pluto. So if you are standing in Pluto, this is your sun. You see only this much. So what is done here is nothing to do with Pluto. We have the laser beam coming from here. There's a mirror which reflects the laser beam. There's a lens here. So the lens is focusing the beam into air, and at that focal spot, air is getting ionized. And so that ionized air is emitting because it is nitrogen and oxygen mostly. So these emissions are of nitrogen and oxygen. So you can see that. Now, as I showed you in the case of carbon, we can have a more controlled environment by having a vacuum chamber. So that's what you see here. So this is the experiment in which you have a vacuum chamber and we have vacuum pumps which can be used to evacuate the chamber to very low pressures if we want. We can go down to something like 10 to the power of 9 torr or so, which is very low. But for our regular experiments, this is not necessary because the plasma is not really very different once you go below something like 10 to the power of -4 torr. So less than that, it is practically vacuum for plasma, irrespective of. It's like somebody said. I mean, when you are in winter in the Western countries, up to something like 4 or 5 degrees Celsius, you can really feel the cold. If it is less than that, you don't really feel anything because your sensitivity is lost. so it's like that. So it's like something like that. So for the plasma, if the ambient pressure is something less than 10 -4 torr, I mean, it doesn't show any difference. We have done this, so we know. So nowadays we measure only from 10 -4 or 10 -3 torr onwards, upwards. So we can change our pressure. What is happening? So you can see some light, a bluish glow there. So that is the plasma. And the laser beam is coming in from here. It is hitting the target straight and the plasma is formed. And we keep our detectors here, at this side. Now it is shown here. It's not shown here. Now our detectors are there. So different ionization processes, the way plasma is formed is like there are multi-photon processes. There is tunnel ionization. There is over the barrier ionization. I am not going into details. And there is something called automotive energy. Once you ionize your target, once you form the plasma, the electrons are fairly free there. And these electrons will oscillate these electrons will be in the grid of the input light EM radiation. And we can think of something called the automotive energy, because these electrons will oscillate like this. The electromagnetic field oscillates at a very high intensity. So if you are using something like visible radiation, visible light, then this frequency is in the order of 10 to the power of 14 Hertz. So that's the frequency at which EM radiation. We don't really think about this because we always talk about the wavelength of light. So, but the oscillation is at extreme high frequency. So these electrons also will oscillate at the same frequency. So they will gain a kind of cycle averaged kinetic energy in this process, and that energy can be calculated, and that gives us very interesting information. For example, if you have an intensity of 10 to the power of 13 watts per centimeter square, which is not very difficult, it's pretty easy to achieve with nanosecond lasers, and if your wavelength of the laser is 1.06 microns, these are some standard values actually. That's why these values are used. This is 1064 nanometers. So then your energy is 1.1 electron volt. This is not really that huge or anything. However, if you change your wavelength to 10.6 microns, this is in the infrared, immediately your electron energy becomes 100 electron volt. This is quite high. And the reason is that there is a term of lambda square here. So this is somewhat counterintuitive, but this is the way it is. When you increase your lambda, the energy of the electron actually goes by the square of it. Now we can think of still higher energies, like it is the same wavelength, but use a much higher intensity, 10 to the power of 19 watts per second. This is quite high. It's not very easy to achieve. But not impossible. In our lab, we can go up to 10 to the power of 16 watts per centimeter square, which is considered high. Now this is very high, 3 orders of magnitude high. But with that, look at the energy. It is 10 to the power of 6 electron volts. This is huge because if an electron has energy of this kind, it will emit gamma rays. Because if it oscillates with this kind of energy, it is definitely going to emit gamma rays. And just imagine where we started with. We start with something like 1 electron volt, because these kind of lasers, we use one particular laser called titanium sapphire laser for making femtosecond pulses. So the titanium sapphire emits at 800 nanometers approximately, and that corresponds to an energy of 1 electron volt. So the photons emitted by the titanium sapphire laser, each photon has an energy of something like 1 electron volt. Now, that is interacting with your target, it creates a plasma, and it gives the electron an energy of 10 to the power of 6 electron volt, which, if you look at it, it is like 1 electron has interacted with 10 to the power of 6 photons, which is again not very normal in our normal circumstances. In normal circumstances, 1 electron interacts only with one photon. That is what we have learned from the textbooks. Okay, so many things happen here. The physics itself is very different from the normal kind of physics that we encounter. So, once that happens, now think particles are going to be very, very different. Like, now there is an acceleration. The acceleration of the electron, which was unfortunate enough to be in the right field here, is like 10 to the power of 17 g. And obviously, these are relativistic kind of fields. So we can expect all kinds of relativistic phenomena. So therefore, the particles accelerated by the laser. So this is called a laser accelerator. So you have a small vacuum chamber, you have a very powerful laser, you generate a plasma, your electrons are accelerated. So therefore it's a laser accelerator. And it attains the same energy in a millimeter, which is otherwise obtained from regular accelerators which need a length of kilometers. So we know about the regular accelerators, cyclotrons and things like that. We know about the LHC, all those experiments. These are really, of course, I mean, they work at a much higher energy. But even a standard cyclotron, a standard accelerator is fairly big. But I can have a laser and a plasma in half the space of this stage, and I can accelerate it to much higher energies than what is possible with an accelerator. And if you look at the cost involved compared to an accelerator, this is much, much less.
Why is it not used in CERN?
Sorry?
Why is this method not used in the CERN in CERN?
In CERN?
In CERN.
Oh, yeah. Oh, I'll tell you why. See, each method has advantages and disadvantages. In an accelerator, you have precise control of the velocity, or you can control everything very precisely. Like, that's the speed of the velocity of the electrons, the angle at which they go. Unfortunately, even now, in the case of laser tabletop accelerators, we don't have that kind of a control. That is number one. Because the plasma formation is a very statistical process, minute variations in the input energy of your laser pulse can totally take things, gives you a result which is very, very different. So therefore, consistency of your results, to ensure the consistency, it was a problem until very recently, but now, as every technology grows, solutions will be found. So nowadays, the consistency is much better than what it was before. So these systems are becoming more and more reliable. But another issue is that the numbers you get from a cyclotron, the sheer number of electrons, number of charged particles you get from a cyclotron, you cannot get here from a laser plasma. So therefore, it has to have its own kind of applications. There are applications. There are some medical applications where this kind of laser tabletop accelerators are being used. So therefore, there is no chance that a laser accelerator, at least in the near future, a laser accelerator may not be used by CERN for their experiments. But we don't know. Perhaps after a few more years, it is not unlikely that will happen. For example, in the case of fusion, laser fusion, all of us might know about it. So the Lawrence Livermore lab in the US, they have been doing this. And there were some reports like, okay, we achieved it. So it was like the case of Higgs boson in the initial days, like, oh, it looks like we saw that, but if you really ask them, yeah, I think I saw that. So it was like that. So, but finally, anyway, they say that, okay, well, now we believe that we have really seen the Higgs boson. Something very similar with fusion also. The fusion experiment is pretty complicated, because you have to use multiple laser beams, several laser beams together, and you have to radiate a very small volume of tritium, I think. And then you have to calculate the input energy and the output energy. So that's the way they decide whether fusion has actually taken place. So from these calculations, they made some announcements about a year or couple of years back, saying that, okay, looks like we have achieved fusion. But after that, we didn't hear anything about it. And the news which came later was that, heads were rolling in the lab, because some of these claims were not right, and the government was not too happy. about the progress of the program because it's eating away millions of dollars and it's not really giving the output which they were hoping for. So these kind of experiments are, they're not very easy things to do. Anyway, so that's the story of the laser accelerator. And now we can think of jacking up our input intensities even higher. So if you go to something like about 28 watts per centimeter square, which is not achievable in the near future by any measure. But hypothetically, once we reach that kind of intensities, you will be shaking the nucleus directly, which means fission, direct fission. But intensity of this kind is not possible at this moment. So I don't know when this will happen. Maybe it will take decades, or maybe it won't happen at all because these kind of systems will need enormous amounts of money. So at these scales, these are political decisions rather than any scientist decision.
So are there any constraints on going beyond what we have been able to achieve till now? Are there any constraints to go to 10 to 28, like scientific constraints?
In a single system, it's very hard to do. Like, in a given volume, okay, this is energy, right? See, increasing energy means increasing size. You can increase intensity without increasing size. Because if you want to increase the intensity, you only need to make your pulse shorter. But energy is energy, so it has to come from somewhere. So therefore, increasing energy means size. So the sizes will be higher. So if you can occupy an entire desert or something for your lasers, probably you can do it. But then, this becomes a very challenging task technologically. Look at the kind of money involved, and even our neutrino laboratory, which India is building now. The current estimate is 1,500 crores. Okay, so that's the kind of money involved. There was another plan for the LIGO, for the Gravitational Observatory, which hasn't taken off yet for various reasons. Similar kinds of money. So, how can scientists justify an experiment of this kind? I mean, we have to. The government is definitely involved in this. They are asking questions. The government is asking questions like, what are you guys doing? What are you doing with the money? Are you trying to excite a nucleus? We give you 100 million and then you excite a nucleus and you write a paper. What is the good for the common man with all this? So, this is a kind of a balancing act. We need to have research, and there's no question about it. For a country to progress, there needs to be research, there needs to be fundamental research, there's no doubt about it. But along with that also comes accountability. Even though output by input is not the only way to measure progress in research, but it is a kind of a balancing act. So various things have to be considered, particularly in a country like ours, where there are many people who find it very hard to have 3 square meals a day. Then the accountability is very, very important. So that's why I said these decisions are political decisions at a certain level, and those could be the constraints which might constrain you in these kind of experiments rather than real physical constraints. Real physical constraints are at the bottom, not at the top. Yeah, when you go down to the quantum mechanical scales, you have physical constraints and the uncertainty principle wins. You cannot really measure anything for sure and all that. Okay, so this is the history of how much time do I have? I think I have overshot. Was it 1 hour? I forgot to ask. So I'll try to finish very fast now. So we can go to the extreme. This is the history of what happened. So nuclear excitation by ions. This is not by light, not by photons. So Ions can excite nuclei, but not photons. We don't have that kind of effect. It's 10 to the power 22. We are sort of there even now. Okay. Now, what is interesting is, when you are about 10 to the power 16, you have magnetic field effects coming. So in our textbooks, we always, dielectric properties of materials, interaction of light with matter, we are always talking about electric susceptibilities and all that. Where did the magnetic field go? Because this is electromagnetic radiation. Why are you neglecting the magnetic field? There's a good reason for this. The reason is that the magnetic field amplitude is given by E over C. So even though in textbooks you see the electric field going like this, magnetic field going like that, that's only a pictorial representation. The magnetic field is in fact much weaker compared to the electric field in EM radiation. Therefore, magnetic field effects will start manifesting only if your intensity is really high. And we know what happens when you have both electric and magnetic fields. So in the electric field, an electron will go like this. The magnetic fields, the Lorentz law, will go like this. It will spiral out. So those things will happen at these intensities, 10 to the power 16, 10 to the power 17. This can be observed, it can be measured. Okay, so X-rays from, how to obtain X-rays from, I have my own results, but it is not there in this talk. So this is some earlier results from TIFR in 1990. It's the way you generate X-rays. Then gamma rays, even gamma rays could be measured, not with much certainty, because that community will not really agree to you if you say that I have 100 counts of gamma ray photons. You need, to be certain, you need more. But anyway, it shows the tendency like that. So, alright, so it's like matter is totally ionized, and the situation is like if you have, you can generate sun if you want it in a very small volume, of course. You cannot have the huge sun in the, or even a small fraction of that impossible. You can have a sun in a volume of, let's say, 100 micron cube or something. That's what you can make. But you can still make it. Then you can have neutron stars, and many things happen. Relativistic effects come to the forefront. Multi-photons scattering, pair production. The photons will fuse together and they'll form particles. Then nuclear excitation, fusion. Anyway, that's what we call laboratory statistics. So the experimental setup, basically we have the laser here, and this is the vacuum chamber, this is your target, and we radiate the target, and finally this is the diagnostic spectrometers and all that, computers, energy meters, oscilloscopes. So all that will be there, and okay, I just skip this. This is the facility we have at RRI. We have almost all the required stuff for doing spectroscopy. So this is a big chamber we made specifically for liquid drop experiments. So right now we have coupled the big chamber to a smaller chamber for solid darkness. That's what we are using at the moment. So just to see the scale of this, it's like my students are actually sitting on top of it and doing some minor maintenance work. This is the plan of that. And so vacuum pumps are required. So there's a turbo pump, there's a dry pump. So you can see the vacuum here. You can see this point is about 8 into 10 to the power of minus 7 torr. That is the pressure which is shown in this gauge. Very slow pressure. And so we have different kinds of spectrometers. These are actually the old ones. So which are more or less out of service now, but we have much better, much newer spectrometers with intensified CCDs, which can actually measure very small amounts of light. So this is X-ray and gamma ray detectors. So we fix all these things into our chamber, and the target also needs to be moved a bit. Between each laser pulse, the target needs to be moved, because once a laser pulse falls, the target surface is etched away, so you have to move it. And then you need to know exactly where it is formed. So we have made our own our own programs in the lab. So this red spot will actually tell us where exactly on the target is the laser beam forming. So, okay, so this is, our interest is to study battery features of a nanosecond and femtosecond LVPs, so I'm not really going into those details. So these are some, okay, I would rather skip all this. So this is the experimental setup. You can see the chamber here, spectrometer. So this is being replaced now with a newer one. So a oscilloscope, very fast oscilloscope, 3.5 gigahertz oscilloscope. 10 years back it was impossible to buy this. The Western countries will not sell this to us, but now they have learned the hard lesson by not giving us the cryogenic technology. You know what happened? We developed our own technology. So now they are very happy to sell us because they are afraid if they don't sell us, we will make it ourselves. So we have this and it's very useful for us. We need that oscilloscope. Oh, well, I will skip this completely because now it becomes more technical and more scientific, and that's not okay. I'll just go to the last slide. Okay. Yes. So this is a plasma, actually image of the plasma at reflexy. See the way it evolves. So we generate it, it evolves like that. We can take photographs. For making these photographs, we need the ICCD, the expensive detector. Because it's not, this video is generated from about 100 or 200 photos which are taken at quick succession. Then it's like making a movie, different frames, you put them together, you get it. It's like that. So, okay, this is these are those photographs. A few photographs. There are many applications for the plasmas. I'm not really discussing them. I just tell you this. So with this I will end. This is one of the major applications of plasma. In olden days, if we go to the moon or something for doing, you need some sample from there, right? To get it back to Earth for analysis and things like that. We can do it even now by using robots. That's not a problem, because now the emphasis is more on unmanned missions. But there's an easier way to do this. You can have a laser LIMS spectrometer, that's a plasma spectrometer in your vehicle. Actually, it was fixed in one of the Mars missions. You can have it, and once you land in a safe place, just point your laser to a suitable rock or something, give a pulse, plasma will come, photograph that. If you have very good cameras and spectrometers, immediately you get the spectrum and beam it back to Earth. So in a moment, in 1 second, down here, we know what is the elemental composition of your rock. So this can be very useful in space exploration. Other applications are in artwork, like time dating of art. This has been done. Very small portions of a painting can be etched out. Nobody will know. People won't even notice because you are taking away from an area of something like 10 microns square or something. Take it out, then you know what it is made of. You can actually do restoration work because most of these paintings in the Renaissance period and all in Europe, they need to be restored now. So first you need to know what is in there before you try to restore, because it's a work of masters and you really don't know what they have used. It is possible to do it. Then estimating the quality of molten metal, many things like that. So acknowledgements to various students I had in the past, like Anija. She is a scientist in GE now after PhD. Jindo is a scientist in Ahmedabad. Sujan Sandeep is doing his postdoc at University of in Germany. She's now doing his postdoc at the University in Australia. There are visiting students. A couple of my visiting students are here because they wanted to hear about plasmas. So these are my previous, just two of my several visiting students who worked in this area. And both of them are, Anup just completed his PhD and he's back in India now. He is still through his PhD. Both of them are university students. And Shafi and Pranita has become a PhD student now. So there are also other students. This slide is a little old, so therefore I had a photo, a collage of all of them, but somehow I missed it. I don't see that. It's not. I think I misplaced one. So thanks a lot, and I'm sorry I took a lot of time for this conference.
What we are talking about, that is 10 to the power of 17G. Will there be the plasma emits any harmful radiation?
Harmful radiation? Up to gamma rays. That's the most powerful radiation we have. And that's the limit, essentially. Whether this is harmful or not is under debate. Luckily, in most of these laboratory experiments, the amount of radiation that comes out is so less that it is not really going to affect us. Even when we were students, girl students were particularly advised not to stand very close to nitrogen lasers, because the nitrogen laser, I don't know the exact reason, this would affect fertility. It was sort of believed that one needs to be a little careful about nitrogen lasers. Here, in the case of plasma, because what we generate in our chambers, particularly the number of photons you get in the gamma ray regime, for instance, I told you, like it's 100 photons and people can dispute that you haven't even observed gamma rays, they can say that. So with that kind of intensities, it is fairly harmless.
Where is it located in the solar system? What is the kind of radiation produced? And what effect does it have on the Earth?
No, this belt is actually around the Earth itself. So for any planet which has a magnetic core, there will be this belt around it. So what happens there is a lot of, because of the solar wind, there are a lot of charged particles in our atmosphere. So they will form a belt because of the effect of the magnetic field. And there are two belts, the first belt and the second belt, P1 and L belt. I don't remember the exact distances of these belts from the Earth's surface, but they exist. For all magnetic planets, this will happen.
How about the laser application in medical surgeries?
There are many applications. Are you specifically asking about the plasma application or the laser in general?
No, they advertising something in cataract operation,
Yes,
laser
yes.
operation, and even in surgery they use the laser.
Yeah, it is called LASIK. LASIK is one of those versions of cataract operation. So what is done there is very carefully measured amounts of laser radiation is used. It is focused in your eye so that the cataract, which is a layer in front of the retina, it is removed. It's very carefully removed. The advantage here is you don't really need to use any knife or something. That was the way it was done earlier, no? Because the eye is so small and the surgeon can make a mistake, and it can be a very costly mistake. So the laser surgery is much more safer compared to that, because medical lasers are a different kind of beast compared to academic or industrial lasers. The primary aim in a medical laser is energy output. It has to be very carefully controlled. So the surgeon will make sure, there are technicians, they will make sure that the amount of energy that goes in your eye will only remove the cataract and nothing else. Because what is used here is more of intensity than energy. The intensity is used to remove your cataract, not the energy. If you have more energy, that will burn your eye. Here the energy is less and time interval also is less. So energy divided by time gives you high intensity here. It doesn't burn your eye, but it removes your cataract.
Sir, how do you manage the super high temperatures that you produce with the plasmas? Do you have any coolant system also associated with it?
Super high temperatures, managing this?
Yeah. How do you?
Okay, we have a chamber with a certain volume, and your plasma, it has only a volume of something like, microliters. That's all. It's not even milliliters. That is one thing. So that, the energy can easily dissipate. Second thing is the degree of ionization in these plasmas. Laser-produced plasmas have a low degree of ionization. They hardly ever go anything above 10%. So therefore, even though these high temperatures are the calculated or measured temperatures of your electrons, if you have 100 electrons, only 10 electrons have that kind of energy. And that is really on the higher side. Our plasmas for even like 3 or 4 electrons only have that kind of energy. And there is something called electron-electron thermalization. So in a collection of electrons, if a few electrons get a high energy, it gets distributed immediately in the surrounding electrons. So because of these two reasons, we are not affected. Of course, we are standing outside. This is happening inside a vacuum chamber. So even if you want to, you cannot put your finger on. If you put your finger there, in front of this laser which causes plasma, you will definitely get a burn. And if it is your eye, it is gone. I have friends who have lost their eyes, scientists.
This lightning creates a plasma. From where this lightning happens and why is there any way to prevent this lightning destroying so many things in the nature?
Preventing lightning, I don't know, people are thinking about that. But I don't know whether this is possible or not. Lightning happens because clouds get charged. So these clouds are huge. So when they get charged, the electrostatic charge these clouds carry in them is unbelievably large. So then, when it finds a path to strike, when it finds a path to get neutralized, it will strike. And because this is extremely high voltage, like 20,000 volts, 200,000 volts and all, the way it goes, it will simply ionize that region. That is what happens.
Unlucky people will die because of that.
Yes. Oh yeah, they will be charged. Because
most of the studies that I found is purely academic studies that is going on in RRI.
yeah.
Is there anything that you are doing application oriented also?
Well, not here.
Which lab in India is doing? What kind of applications?
There are labs. See, it also depends very much on what is your mandate. So there are laboratories in our country which do application oriented approach. NAL is an example because I have met people from NAL, excellent, technically super these people. What I would say is, there is no dearth of talent in our country, but there is a problem with management. Seems like you have a lot of talent, but this talent is not utilized. There are no clear directives. It is like you are given a lot of money and you are allowed to do what you want to do. Finally, nobody is asking you any questions. So what do you do? The very same people, when they go to the US, they are so successful, right? See, there are a lot of critique about our education system and all. I don't believe on that, frankly. Because if we now go to the US and see who is actually running their laboratories, who is actually running their universities, Indians and Chinese. It's a fact. But the same people cannot do a fraction of that in our own country. The reasons are political. The reasons are not scientific or anything. We have enough and more expertise in our country. Our education system is not too bad. At least the good places are good. I'm not considering here the numerous number of engineering colleges which are on capitation fee. Just exclude all those. But there are good places, and our people are very brainy. There's no doubt about it. Indians are intelligent, Chinese are intelligent, Russians are very intelligent. So it's only the question of the environment. And for us, if you ask me, We are one of the institutes which do very well on our mandate. Our mandate is basic physics. It was founded by C.V. Raman. Raman was not an applied scientist. So historically and traditionally, the mandate of RRI has always been fundamental science. That we are doing very well. I'm very happy to tell you because there are metrics which we can use. In one of my other talks, actually, I had that information, but it's not here, fortunately. So that way we are doing very well. I mean, there are institutes like TFR, for instance, who are doing very well. So it is not that we don't have enough talent. And I should be very fair to the government. I mean, until now, the government has been very liberal. Our funding is very liberal, actually. But now, to be precise, from 2 weeks back onwards, there are some indications that things might change. So
any possibilities to make use this lightning energy? I mean,
I don't know the details, but this is something people have been thinking for a long while. Like, if you can just harness the energy in one single lightning, it can run a city like New York for a year. But how to harness it? Because it's so powerful. How to do it? There is no solution to it even now. Single lightning.